In this video, we'll find the formula for the nth Fibonacci number. So the Fibonacci sequence is defined by a recurrence relation. F sub 0 is 1, F sub 2, F sub 1 is 1. And then for n greater than or equal to 2, f sub n equals f sub n minus 1 plus f sub n minus 2. So you just add the two previous numbers to get the next number. The question is to find a formula in terms of n for the nth Fibonacci number. Well, this is a recurrence relation, a linear second order linear recurrence, and we know how to solve this. So we write f sub n minus f sub n minus 1 plus minus f sub n minus 2 equals 0. And we follow the procedure that we had before, which is we find the solutions of the form r to the n, where r is not 0. So we get r to the n minus r to the n minus 1 minus r to the n minus 2 equals 0. And then we divide everything by r to the n minus 2, and that gives us r squared minus r minus 1 equals 0. And then we find the roots of this. So we use the quadratic formula. We get negative b, so that's 1 plus or minus the square root of b squared. That's 1 minus 4ac, so 4 times negative 1 over 2a. That gives us 1 plus or minus the square root of 5 over 2. And these are real numbers. So the general solution is a sub n equals, or f sub n is a times 1 plus root 5 over 2 to the n plus b times 1 minus root 5 over 2 to the n. Now we need to plug in the initial values to solve for a and b. So if we plug in n equals 0, we're supposed to get 1 equals a plus b, right? Because when you plug in n equals 0, then these terms here are just both 1. So you just get a times 1 plus b times 1. That's a plus b, and we're given that f sub 0 is 1. Then we plug in n equals 1, and then we're going to get something more complicated. A times 1 plus root 5 over 2 plus b times 1 minus root 5 over 2 equals 1. Okay, it equals 1 because we're given that f sub 1 is equal to 1. So now we have to solve this system of equations for a and b. Well, it's actually not that bad. One thing we could do is we can take the first equation and get that b is 1 minus a. So then we substitute into the second equation. I mean, it's just like solving any system of linear equations. So it's 1 minus a here, 1 minus root 5 over 2 equals 1. It's just a bit messy. You're going to get a times 1 plus root 5 over 2, and then minus 1 minus root 5 over 2, and then equals 1 minus root 5 over 2. So that's going to give us a times root 5 equals 1 plus root 5 over 2. So a is equal to 1 over root 5 times 1 plus root 5 over 2. And then we solve for b, so b is 1 minus that. Is there an easier equation we could work with? Not really. We get 1 minus a, so that's okay, let's just write this out as 1 plus root 5 over 2 root 5. I'm not sure if that makes it easier, but it's 2 root 5 over 2 root 5 minus 1 plus root 5 over 2 root 5. So this is going to be negative 1 minus root 5 over 2 root 5. And we can write that as is that wrong? Let's see. Oh, no, it's plus root 5. And we can write this as, well, that's what b is. Yeah, that's what b is. We can just factor out the root 5 and get negative 1 plus root 5 over 2. So that's b, and we have a, and then we know, so f sub n, the nth Fibonacci number, is a times 1 plus root 5 over 2. So, well, that's going to give us, no. It's a times 1 plus root 5 over 2 to the n. And we have a is equal to this. And so we actually get 1 over root 5 times, see, we have another factor of 1 plus root 5 over 2. So this is going to be raised to the n plus 1 power. And then we have a b, which is 1 over root 5. I'll factor the 1 over root 5 out. We have b is 1 over root 5 times negative 1 plus root 5 over 2. And that is, I can actually factor out a negative. Let's factor out the negative to make it a bit nicer. So we have a negative out, so it's going to be a plus, and then that's going to be a minus. That gives us a 1 minus root 5 over 2. We have a 1 minus root 5 over 2 here, right? So then we're going to get a minus 1 minus root 5 over 2 to the n plus 1. So that is a closed form for the Fibonacci numbers. And we solve this using the strategy for solving linear recurrences. So it's pretty remarkable that this right side is actually an integer, but we know that the Fibonacci numbers are integers, and so these are all integers for n an integer. Probably not the most useful formula, to be honest, but it's kind of nice to know that there is a formula for it.